would like now invite Professor Sriraam Natarajan, who will be talking about human-allied sequential decision making. So, but to just give a brief background, Professor Sriraam Natarajan is a professor and the director for Center for Machine Learning at the Department of Computer Science at University of Texas, Dallas, and also he is also an RBDSCAI distinguished faculty fellow at IIT Madras. His research interests lie in the field of artificial intelligence with emphasis on machine learning, statistical relation learning, and AI, reinforcement learning, graphical models, and biomedical applications. He is a AAAI senior member and has received the Young Investigator Award from US Army Research Office, Amazon Faculty Research Award, Intel Faculty Award, Xerox Faculty Award, Verisk Faculty Award, and the IU Trustees Teaching Award from Indiana University. He's the AI and Society Track Chair of AAAI 2022, Demo Chair of IJCAI 2022, Program Chair of SDM 2020, and ASEM COTS COMAT 2020 conferences. He was the specialty chief editor of Frontiers in ML and AI Journal and is an associated editor of MLJ, JAIR, DAMI, and Big Data journals. With this brief background, I would like to invite Professor Sriraam Natarajan to deliver his lecture on human-allied sequential decision making.
Thank you for the invitation, and thank you for the kind introduction. Can I share my screen, if that's okay?
Please.
Okay. Can you see my screen?
Yes.
Okay, great. So thank you for the very nice introduction, and thank you for an exciting day. It's very hard to follow the previous talk. Follow as in coming next to the previous talk, because there was such a great talk by Professor Rick Thomas. So I'm taking a slightly different view in my talk here, where I'm assuming that the human knows their plan, human knows what they want, and the question is, how can a sequential decision-making agent interact with a human and use the human as an ally in improving its efficacy as well as efficiency in solving and generalizing to new problems. As Professor Srinivasan introduced me, I am Sriraam Natarajan. I'm with the Center for Machine Learning at UTD, and I run the Starling Lab. So before I start, I should really thank my students, without whom any of this work is not possible. Specifically, I want to call out three names: Harsha, Mayuk, and Philip. For their work is what I'm going to cover in today's lecture, and along with my key collaborators, Gautam, Ravi, and Prasad, for their inputs in the problems that we're going to talk about. So thanks to the many funding agencies and companies who have been working with us for making these things happen. So the big vision for our lab has always been on building human allied AI. So in my head, what does human allied AI mean? Human allied AI refers to the problem of building intelligent systems that can seamlessly interact with, learn from, collaborate, and once you learn enough, potentially teach the human expert. So these are AI systems that should exist in the world in the presence of human. So they are not just like, aware that the humans are present, but they can actually use the knowledge, use the experience of the humans in learning better models. Okay, and I'm going to focus, and as I keep iterating over the talk, we do this in the context of many different machine learning paradigms, but I'm going to focus primarily on sequential decision making. So that's the problem of human allied AI. And so to give you an example, as Professor Srinivasan mentioned, many of my focus area has been in medicine. We work with a whole bunch of problems, all the way from predicting, there was somebody who joked about this. We were predicting birth, like preterm birth, all the way to predicting death due to cardiovascular events. And we try to look at problems in between a lot. So we work in the whole spectrum of medical with medical experts. And that's actually the reason I feel motivated to do this human in the loop learning, because these medical experts are true experts that we work with. And their knowledge should not be used only for labels. So the agent we call as the statistical relational learning, or Starling agent, exists in the world. It's going to talk to the medical experts. Like Professor Rick Thomas mentioned, we should be able to explain our plans, explain our decisions, explain our policies, explain our predictions in a clear, human understandable manner, not in a machine learning manner. I can just throw, let's say, a deep network architecture and say that these are the weights in these layers, right? And then you go figure, right? So you can't talk like that, but we have to talk in the language of the domain experts. And I'll give you some examples as we go through. And what we do is we observe the feedback from the medical experts, and then we take actions in the world. So remember, the medical experts also take actions in the world. So the system could ask this question: hey, why did you prescribe this person a steroid? He has diabetes. And the medical expert could say one of two things, right? The medical expert could say, oh, I didn't realize it. Thank you for bringing it to my notice. He was distracted. He didn't tell me. He was on his phone while I asked him these questions. So now I fixed it. Or the person could say, I know this, so I'm going to just bump up his insulin or his metformin, whatever he's taking. But he needs the steroid because he's in acute pain, and we need to bring that down. Okay, and this is a conversational stuff where the system could provide a suggestion, but take feedback from the human expert in the clinical terms, not in terms of weights of a neural network, right? So we should be able to do this as, again, one of the most important criteria here is that things need to be explainable back to the expert. So with this kind of background, I'll start talking about the types of problems we are looking at. Oops, sorry. So for instance, one of the most important problem that we have always looked at is this notion of assistantship learning, where the system exists inside the computer, whatever the AI agent exists to assist the human. So the set of actions of the agent could potentially be a subset of the action of the humans, or it could be a little bit more too, could be completely distinct, maybe bringing the relevant resources, pulling up relevant records, performing relevant search, and so on. So it could be any of the two. But the goal is explicitly fixed. The human is doing the job. The job of the agent is to assist the human. The second case is where the agent is going to learn to imitate the human. So it's an apprentice. So it's like a master-student type education. So the human is the Jedi master, and the human agent is the apprentice that's learning from the master, right? So it's going to learn and figure out how to solve the problem. So it's going to do that by, like an intelligent student, asking intelligent questions, not at every point. Remember, again, one of the reasons we go for techniques like active learning and other learning inside machine learning is because the human time is very valuable. So if you keep asking so many questions, then the human is going to shut off the system. Remember Clippy, people who are old enough can remember Clippy from 90s, right? We all closed it because it was just too annoying by asking way too many questions. So the goal is not to ask the right number of questions in doing this. The third setting, which we have recently worked on, is the notion of collaborative problem solving, where the human and the agent together solve a problem. So they work together as a team. The agent may spawn off, do a small set of subtasks by itself, or it could work hand in hand with the human and try and solve this task together. So that's the notion of collaborative problem solving. So the notion of human-allied AI for me encompasses all these different types of learning. And for this rich human-allied AI, in my head at least, there are three important steps. The first is underlying learning, which is the foundation, should be very strong. So we need methods that are effective, efficient, that can generalizable, but learn only from data. So we don't really think about knowledge in the first step, but the point is that we build efficient learning algorithms. Think of classical deep learning, deep reinforcement learning, classical planning. The goal is we need efficient learners and reasoners as a foundation. Second step is where we allow for rich human input. So the humans can specify things that are just more than labels, right? So they can give what is called advice, guidance, feedback, suggestions, and we should be able to take that and improve the learning. Okay, the third step, which is the top step of the ladder, is where we close the loop. So the agent should know what it knows and ask relevant questions about what it does not know. So the difference between the second step and the third step is, in the second step, the human observes what the system is doing and then gives feedback. Okay. In the third step, the agent can reason about what it knows. It can reason about what it is uncertain about and ask questions about what it is most uncertain. Okay. This, in my head, is what really achieves the true human, the student-teacher interaction. this true human AI collaboration can be achieved only if the system knows what it knows and asks question about what it does not know. Okay, and so what is the side effect of this? I firmly believe this, and we have some empirical results in our papers. You will come up with some surprising discoveries that you can teach back to the human. The AI agent can come up with some surprising discoveries that it can teach back to the agent. What I'm not going to do in this talk is really focus on the first one. Okay, so the first step is not the focus of the talk. I'm only going to focus on the second and third steps. But I just do want to say clearly that we have significant prior work in the first step. Okay, so we worked on probabilistic graphical models, relational models, reinforcement learning, partially observable MDPs, inverse reinforcement learning, planning. So we have had a lot of experience on building the foundational stuff, primarily based on our specific method called gradient boosting. Relational gradient boosting, and we have an excellent software that's publicly available that people can download and use, and that works great. And we've adapted these techniques. I don't like the word applied these, because application merely seems to stick. It's just take this algorithm, give the data, and it should work, right? It just never works. So I like the word adapt a lot. We adapt these algorithms to many of these real problems: electronic health record data, clinical studies, imaging. As I kept saying, we are really working with a lot of physicians. We work with the cardiologists, neonatal ICU, NICU physicians, pediatric ICU physicians. We work with gynecologists, OBGYNs, mental health experts. So the whole spectrum. We work with a lot of medical experts. And so we get a lot of amazing knowledge from them that we can use to bias the learning algorithms. Okay, so I'm not going to focus on this step. I just want to just tease you with the idea that we can do this effectively and efficiently. And these models are quite generalizable to newer problems. We have significant publication record in this aspect. But I do want to encourage, if you're interested, to look at our lab webpage, and the code is out there. And of course, we have a running tutorial that we keep updating pretty much on a weekly basis. And we push all our code of every paper that we have written in the last, I guess, 10 years or so, has been released as code in this GitHub. So we have everything there. And so you could take a look at this. With this caveat, I guess I have another 20 minutes or so. And so what I'm going to do is I'm going to jump right in this notion of advice taking and the notion of closing the loop. Okay, so how can human knowledge be taken into a learning algorithm? So that's what I'm going to talk about. Again, we have done this in the context of several learning algorithms: probabilistic graphical models, relational probabilistic models, reinforcement learning, inverted reinforcement learning, imitation learning, planning, and of course neural based models as well. So all these models have can take rich human advice, and I'll talk about what this advice looks like in a couple of slides. But the point is that they are not just taking the data. Just taking the data. I love this quote by Tom Mischel. If you take this legendary 1997 book and you look at it, I think it's section 1.3. It says the futility of bias-free learning. If you allow a learning algorithm to not have any inductive bias, the word bias has a different meaning in societal terms and a different meaning in machine learning terms. If you take a machine learning algorithm and not bias it appropriately, then you could come up with an arbitrary hypothesis that beautifully explains your training data. For instance, if I'm predicting who's going to pass an exam, the system, and just have cameras observing people, then the system could say, well, anybody who wore a blue shirt passed in that exam. Okay, oh yeah, by that criteria, I will pass. But the point is that anybody who wears a blue shirt could pass the exam. And that's a perfectly reasonable explanation for the training data that was provided. But that's not true for the domain, right? So that's where the human comes in to appropriately bias the learning algorithm, okay? But what I'm going to do is I'm going to look at this from the context of sequential decision making. And by the way, sequential decision making itself inside AI and machine learning is a broad field. It's not just limited to reinforcement learning as many people think, right? So you have probabilistic planning, where, for instance, the goal is I give you a goal that is semantically well defined, and then maybe I give you some operators, and then you start figuring out what the set of sequence of actions or a plan that leads to the goal. And there is so much work on that in the context of planning. I mean, it's a whole subfield by itself. It will probably take a year or two of courses to teach the planning algorithm development. Of course, reinforcement learning, which, as you know, is going through its huge second wave right now because of the success of deep networks. So reinforcement learning is where simply stated the goal is to find a sequence of actions that maximizes some notion of expected reward or expected utility from the environment. There is also a subfield of reinforcement learning called inverse reinforcement learning, where the reward function, the utility functions, is not directly given to you, but they have to be inferred based on the trajectories that you get from the expert. So it could be, for instance, teaching a kid how to drive a car. You drive a car and then you say, "Oh, I did a mistake here. I braked too hard, or I was too close." And then the kid builds a model on what it means to brake and when to brake and how to brake. So that's really inverse reinforcement learning. Observing the human expert do something, then figure out what are the utilities and trade-offs, and then act accordingly. Imitation learning is where I don't really think of a notion of the utility, but I look at the successful completions and then figure out what the human did to successfully complete something, right? So for instance, I'm going to zoom in a little bit on inverse reinforcement learning for this first part, where I said, look, I've given you that the set of state action sequences. So human has been in a particular state, executes a bunch of actions. So maybe playing chess, driving a car, and so on. And the goal is to figure out if the agent can induce this reward function. So in IRL, the assumption of observing reward at each step is kind of relaxed. Instead, we assume that there is a human demonstrator who shows how to act in the world. The rewards are then induced or regressed or reasoned from the demonstrations to determine the optimal behavior of the agent. But the key assumption here is that the demonstrations are good. Okay, but remember that the demonstrations are not good all the time. For instance, many of the times we have seen people, let's say, run through a red light signal, like right when the yellow becomes red, people just rush through it. But if there is a kid in the car, they immediately turn and say, "I know I did this, but you can't do that," right? So that's a typical advice we always get. I mean, I'm a dad, so now I do the same thing. I tell my kid, I can do it, but you cannot, right? The point is that it's kind of like acknowledging that the trajectory is a mistake, but the intent is not. So it's like, I took a sharp turn. Hey, I know I took a sharp turn, but you cannot do that. I did this, you cannot do that. I dropped the class, you can't do that. So the point is that the human can make mistakes, and if you're just allowing the AI agent to infer from that, the AI agent is probably going to make those mistakes too. To avoid that, the human can say, "I can do it, but you can't do it," or "I made a mistake, you don't do it," right? So explicit feedback on what is right and wrong. So what we have done is we have started including this, right? So instead of just having trajectories and then go to the learner from there, I hope you can see my pointer. If not, let me just switch on my pointer. So explicitly just having these demonstrations and inducing the reward function. Instead of doing that, we also get an advice from the expert. So what does this advice look like? So for instance, in a simple case, let's say I'm starting in this grid location and I want to go here, okay? And imagine this grid with all pits and gold and all that stuff that this system can navigate through. The human can say something like, when you are in this state, the preferred action is to go diagonally. Avoid action is going up or to the right, because going diagonally will get me in one step to the goal, whereas these two are not the preferred actions. But the human could have done it because they were exploring to see what is there in those states, and then they figured out what is right. Okay, so a simple state action becomes an advice. And what this tells you is that the value of doing, the utility of doing, the expected utility rather of doing, going diagonally up is better than the value of going straight up or to the right. Okay, so that's what this equation gives you. Again, for the purposes of this talk, ignore all the equations, but I mean, I'm hoping to get the big picture in. The point being that instead of just providing demonstrations, we can provide such advice. And you can also give this in terms of state advice. It is preferable to be in this orange region than in the blue region. And you can give this in terms of the state advice, and they can be translated into the objective function. And what we have shown is that you can write out this as a linear program. Again, ignore the math and details, But the point I want to drive here is that this is a combination of what the data, the demonstrations tell you, plus what the advice tell you. It becomes a nice, beautiful linear combination of, okay, what happens if I follow what the data gives me and what my advice tells me. Remember, advice may not be applicable everywhere because it's very small number of advice that the human has given. And then what we can do is we can now trade off between the data. So if the data is noisy, advice helps to do it better. If the advice is not perfect, the data can help fix it. Of course, if both are imperfect, then the system has to explore and learn. That's a different problem. But at least if one of them is reasonably good, then we can get to better results. And what we have demonstrated this is we have evaluated this on many domains, but I'm just showing this on 4 domains where this is about navigating a grid world while avoiding obstacles and avoid getting killed. This is the state advice. These are 3 types of advice. One is on states, one is on actions, one is directly on the reward function. Okay, and this is the blue part is the learning only from data. And what you can see very clearly is that the use of human knowledge means we are achieving better. By the way, in these 3 domains, higher means better. This is the traffic signal domain. Higher means worse because higher means there are many cars stuck in a signal. This is a domain that I came up with where there are some traffic signals near a highway and you want to avoid the congestion. So it's basically the optimal switching of these traffic signals in such a way that you avoid congestion from a highway or to a highway. And so here, lower is better. You can see that using advice means that the wait times for the cars is actually much lower than just observing the data. So the common denominator in all these is don't just use the data, but also human input on top of the data. But I gave you very simplistic notions of what these human advice are, but this can be much broader, okay? And purposefully, I'm switching problems to show the versatility and the generality of this approach. So think of a simple problem. Let's say I'm interested in building project teams. Okay, so I'm building teams of projects, and in these teams, I can come up with many types of advice. I can say that, look, form teams such that they have high publication record, because higher publication leads to higher successes. You could also talk about class imbalance, precision versus recall, false positives versus false negatives, and figuring out how to stop that. You can have privileged information. While forming teams, you can say, look, these 2 people generally don't work together, so don't put them in the same team. Or, these 2 subgroups are not fans of each other, so maybe try and keep them apart. Generalization, you can say things like similar groups will have similar members. Then you can start introducing fairness, ethics constraints as well. You can say things like similar individuals should be treated similarly, but there are some class merit-worthy people who should not be discriminated. You have to make sure that these merit-worthy people on the outside, while they don't look very attractive, they have some merits that you have to look into. And you have to say that there are some vulnerable population, vulnerable groups, and you should protect them as well. And you can also say that the teaming should match between the human and AI. So if a human is going to do the matching and the AI is doing the matching, we need to get them aligned with each other. So the point I'm trying to make is that we can have all these types of rich constraints that are not specific to a single example, but that are broader in terms of what can be provided. And they are not as simple as I prefer this state to this action to this reward. So what we have done is in our set of publications, we have covered many of these types of constraints in our learning algorithm. Actually, many of this can be done in, using this notion of preferences. You can basically define preferences over states, over features of states, over features of the problems, over attributes of the persons, and then you can incorporate all these constraints in the learning method. So what I've done so far is just given you an idea of what are the types of rich human information that can be obtained. So now what I'm going to do is try and close the loop, see if the machine can actually seek advice. And why is this important? Because one thing is always true, right? If I ask somebody, what is the one thing that you can get for free from anybody? The answer is most likely advice, because people give advice for free all the time, right? It's like, and the best is when you actually learn driving. You have 4 people in your car, man, your head explodes. Everybody gives you a feedback, right? And it's like, you should not drive that fast. You should not roll through that stop sign. You are so sleepy. You're texting while driving, even though your phone would be somewhere else. right? You're running that light, you're driving that fast. So everybody is giving you advice at the same time. So the question is, which is the most important? Okay, it's kind of like my 5-year-old kid. I realized this like last week when I was giving him 5 or 6 instructions. He actually turned to me and he said, "Shh, Appa, shh." I said, "What?" He said, "Shh, I will ask you. I will ask you if I need something. You don't tell me everything. Wait." So that gave me this flash, like, you know what, this is what I've been telling my students that we should be doing in computers, and then my kid teaches me that this is what I should be doing in real life as well, right? So the goal is, and our hypothesis is that if you're only learning from examples, you let's say you need n examples. Okay, it's been proven theoretically that if I perform active learning, by which a system chooses an example for the human to label, then you can actually reduce the number of examples required to some logarithmic. So you can do log n examples. Again, in 90s, people have shown that if you get strong, good advice as inductive bias, search bias, whatever bias you want to put in your learning algorithm, that can also logarithmically reduce the number of examples. One hypothesis that we are currently working on proving is if I combine both, where I'm actively getting this advice. So basically the system is saying I am learning, but while I'm learning, I don't know what I'm doing. I'm going to ask you for specific states. So in the previous case, when I gave you, looked at the grid world and gave the advice, all the advice was given before learning. Here, the advice is going to be obtained during learning, during execution by the system. The hope is that we will reduce to log n. So even achieve a more exponential decrease in the number of examples. So as an example, you take the same inverse reinforcement learning. What we have done is, in the context of, say, drone flying, we have figured out how the system can ask questions by simply doing the following. What we did was we clustered the groups of states into groups, and then figuring out which of the states the system is most uncertain about. So you explicitly compute this uncertainty over the state and solicit advice from that. And our paper, the 2016 paper, 2018 paper, and now we have another paper on this. You can look at these results. Basically, it does reduce the number of examples needed drastically. And I'll give you some results in other formalisms. But again, from just the active advice seeking, the idea is very simple. Find the states, but don't ask advice for one state. Because if you ask advice for one state, you won't know how to generalize. So figure out a way of generalizing by grouping the states that you are most uncertain about. So let's talk about a traffic signal domain. There are 2 signals. Let's say there are many signals. And then now I can say, well, find the signals that are closest to the highway. Maybe ask a question about them first. Once that uncertainty is taken care of, maybe the ones that are maybe 2 steps away from the highway, 2 signals away from the highway, ask questions about them. So what you're going to do is you're going to now methodically increase the complexity of your questions, and then you can learn based on that. But remember, sequential decision making is not simply inverse reinforcement learning. It also includes other things like planning, and of course we have worked on other formalisms that combine several of them. And one of them is this notion of planning, right? As I keep saying, planning is such a big, where I can have pretty much a hierarchical decomposition of the problem that you want to solve. At the highest level, it could say travel to India, say from Dallas. And then I'm going to break it down to buy tickets, check for COVID policies, and then blah, blah, right? And then go to the airport, right? Go to the airport now has take your car, drive to the airport, check in, get to the gate. Then driving to the airport has, again, I can break it down to go from here to the first signal, blah, 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 to the parking spot. So the point is that humans are great at decomposing a higher level task into a sequence of subtasks. Planning systems can do that too. A classic example is hierarchical task network. And here, what we did was we basically did simulations, and we can compute at every point what is the most uncertainty. So I'm going to say, between my driving to the airport and COVID policy, where am I most uncertain about? Well, driving to the airport nowadays seems to be okay for me. I've been in Dallas for 4.5 years. So now I know how to get to the airport. Not a problem. COVID policy, on the other hand, I have a lot of questions. So I'm going to ask the person. So what I try and do is I figure out which of the subtasks I have the most uncertainty about, and I ask questions. And we did this on I think we ended up, I'm showing only 10 domains here, but we ended up doing this over like 30 domains. And this red is our method where we actively ask the questions. As you can see, red basically wins everything. Okay, this is percentage of problem solved. Higher is better. Red wins everything. Green is just purely planning without any human input. Blue is where, like the previous step, the advice is given before learning. And this is some random query strategy. So randomly, I just decide, no, I'm going to ask a question rather than having an informed decision. So clearly, having an informed way of asking question helps. What we have also done is taken that and integrated with an end-to-end natural language system learner, right? This is not just our work. It's joint work with Professor Dan Roth from UPenn, Julia Hackenmeyer from Urbana-Champaign, Jana Dopa from Washington State, and Martha Palmer from Colorado. And what we have done is we have combined this planner with a natural language processing engine where we ask questions in natural English language, right? So a system could say, the person could say, build a tower of 4 blocks. And the system could, and then the person could say, add a row of size 2 on the right. And the system could ask questions like, should the height of this new structure and the tower be the same? Okay, so this is a structure called L. We couldn't get just the L, so we called it ELL, L. And it's asking this question, should the height and height of the tower and height of the L shape, are they the same? And the answer is yes. So here, for instance, the instruction was first build a tower and then add a row. Okay, and now it's asking, I'm just trying to generalize and understand this notion of L. It's a new concept that I'm adding to my language. Should the height and tower be the same? And it can actually ask very smart questions even more, right? So it can ask things like, is the width of the new shape same as the height? Because in this case, it looks the same, but it's not. Okay, is the height 1 more than the width of the new shape? Or is the width 1 more than the height? Should the height be 1 more than the width of the row? So it can ask questions that allows it to generalize from one example. Because when you generalize from one example, from one demonstration, you cannot just memorize it. If you memorize it, it clearly fails. So what we have done is, can we ask the certain number of questions so we can build these concepts as we go? And as you can see in this experiment, this is in a Minecraft building domain. After about 50 or 60 examples, we get to the right way of learning. And in a chemical bonding domain, again, with about 20 examples, we get it right. So the point is that with very small number of examples, with the fact of asking questions, we can do better and better. Okay. How many minutes do I have before the last one?
I think you have about 3 minutes, so that we have about 5 minutes.
So I will try and tease you with one more thing, where the human advice is not restricted to just questions that can be given as feedback, but also a human knowledge can be combined with a lower level reinforcement learning agent. So what we have done is we have taken a hierarchical planning network that is developed by a human who helps define the proper state abstractions for a reinforcement learning. So what do I mean by that? If I'm driving, let's say from, let's say I gave a talk in UIC Chicago, and I'm coming back to Dallas, then my first step is get to the airport, okay? But during that time, as a human, I know automatically, I'm going to only think about my traffic in Chicago. Even though my hometown is now Dallas, I'm not going to think about what is the traffic in Dallas right now. It is completely irrelevant, even though my data tells me what the traffic is, right? We humans are very good at abstracting out things that we do not need while acting. And the question is, how can we define that for RL agent? So in a recent work of by Harsha Kokel and actually Arjun from IIT Madras and Professor Ravindran from IIT Madras, Professor Tadepalli from Oregon State, what we have done is we have combined a higher level planning, which defines these called abstractions, things that are not necessary for a lower level reinforcement learning agent effectively. So what we can do is we can solve problems faster if we figure out how to use the human knowledge, saying, look, when you are driving, when you are driving from here to here, all the traffic here doesn't matter. Maybe the traffic even 30 miles out doesn't matter. Only the traffic on 90 matters. And how do you do that? With human knowledge, by having a plan. Okay. And so what we have done is we are basically defining plans at a higher level that allows us to abstract out and create small reinforcement learning problems. So this big reinforcement learning problem is now created into is now chunked into a small set of smaller reinforcement learning problems, which when solved sequentially allows us to solve the big problem at the higher level, right? So again, I'm not going into the detail for the lack of time, but obviously it works great. Otherwise, I'm not going to talk to you about this here. As you can see, the use of a planner as against directly using just the reinforcement learning, you get much higher reward. And the most important thing is, because planning is much more generalized, we can transfer efficiently across tasks. We can generalize better. We can reason about other objects, other domains. And what we are recently working on, and this is under preparation, is extending this work with deep reinforcement learning underneath, but a higher level reasoning agent at the top. So it's like how we think, right? We break problems into small problems, and then our motor control takes over, right? All I'm thinking is go pick up the kid from the school, okay? And then it's muscle memory. My car, I don't even remember starting my car. I don't remember taking this turn, but your muscle memory kicks in and you solve it. But at the higher level, we are breaking down the problem into smaller problems. And that's what we are doing here. Have the human break down the problem to smaller problems, and then reinforcement learning agent can automatically take over. So I'm going to conclude by saying that sequential models that are not simplistic are extremely important in real problems. Human is an ally, although people like Elon Musk wants us to believe that AI is going to take over the world and destroy everything. I think the bigger risk is humans than AI. So I'm going to say that human is an ally to an AI system. And having worked with several medical experts, I can confidently say that if we have a good AI system, then we have excellent human allies who are ready to help the system, help them do better. Okay. The most important thing is, I've reserved it to the last. When you talk to a human, communication is extremely important. Okay. Like when Professor Rick Thomas uses the word model, I'm pretty sure he has a slightly different meaning of what the word model is from what I have to what, let's say, somebody in advertising has. So we have three different notions of what a word model is, and we are just three humans, all right? And the same thing, right? If I talk to, forget somebody outside computer science, high performance computing person has a different notion of what an algorithm is than a machine learning person. Okay, for them, I have spoken with a HPC person who said, give me an algorithm. I gave belief propagation, and they said, that's an application. That's when I realized what I call an algorithm is their application. Okay, and what I call an application is actually the algorithm for somebody else. So the point is that communication is extremely important. So we have to fix the communication with the humans upfront. And that's where natural language is a little bit difficult. So we need to have formal representations that work with natural language, fix these communication gaps, and that's when we can learn. And so, of course, there's miles to go before we sleep. We want to deploy this in medical domains. Specifically, I'm looking at building intelligent assistants that can reside in electronic health records, and that's my current goal. Of course, social science, graphics, and journalism. And now I'm working on what is called science of science, or data science genome, where we are really interested in, if a new student comes in and says, hey, I'm interested in this particular topic, what can I read? Not just list the most popular people, but I want to give you a proper growth of this area, right? So many people seem to think that machine learning is only 5 years old, okay? And so I want to show that, no, there's been a body of work starting in 1950s, and here is what they are, okay? Learning from multiple experts, like what Professor Thomas said, ability, and I want to really start including ethical constraints, fairness constraints in learning, of course, multiple modalities of communication. Natural language is only one such way. There is gestures, there is, other modality like, dragging and dropping and so on and so forth. And finally, of course, my goal always has been, how can we teach back to the human? Okay, so I'm sorry if I ran a little bit over, but feel free to ask me any questions. You can, of course, tweet. That's the barcode for our lab webpage. Everything that I spoke now is available in my lab webpage. With that, I'm ready to take questions.
Thank you so much for an energetic talk on this human-led sequential decision making. So, before I take up, I have some interesting question. I think that's interesting to me to know the answers. Like, you talked about, cognitive assistance. I mean, intelligent assistance as in cognitive assistance. So, what are your current works or, recent takes on explainable AI in cognitive assistance, and how much mature the field is?
When you ask me how, maybe I answer the second one first before the first one, right? Because the second one is how mature the field is. I think there's always a lot of rooms of improvement, right? So I think when you think of even cognitive assistance, currently I feel like we are still not explaining the models as clearly as we should be. And that is because of the fact that the models are evolving on a regular basis, right? Many of the domains have gone from simple handwritten cognitive assistance from back in 80s to people are now even using deep neural networks to model the human decision making, and that makes sense. And so the explainability is an evolving problem. Again, right? Explainable AI might look new because it's kind of got a second wind. But just as an FYI, my postdoc mentor Jude Shavlik did his PhD thesis on explanation-based reasoning learning in 1985. And so did my advisor, Prasad Tadepalli, actually 1987. And Prasad graduated in 89. And they both had theses on explanation-based learning. Stuart Russell had his thesis on explanation-based learning back in 1985. So this is a very old problem that people have been thinking about in explanation-based learning and explanations inside AI. So it's an evolving field. So that's the answer. Like for 35 years, we've been doing this problem. So it's still not matured yet. It's an extremely important problem because when you start building these cognitive assistants, the old BDI framework, the belief, desires, and intentions, I think that holds the key. To me, that holds the key, because when I'm building these cognitive assistants, I have to figure out what and let's say I'm the assistant for you, right? I'm the AI agent. I always like to pretend like I'm the AI agent, and you're the human, and I'm trying to build these cognitive assistants. I have a model. I have some beliefs over what I know about the world, but I should also have beliefs over what your intentions are, right? And what your desires are, and your beliefs are even. So once I have a model of your BDI architecture, and then I have my own, then I have to figure out how they map. And there's a lot of work left in that area. There's a lot of gap in that area. And I think that fundamental research in other ways, in other problems like POMDPs, efficient learning, efficient reasoning, efficient inference, I think they all will move the cognitive assistance as well forward. So to me, the field needs a little bit more, a lot more maturity before they can actually be deployed, if I can answer that way.
Okay, that's what, because I was curious because I've started looking at that area, so I just wanted to.
Oh, it's an amazing area, yeah.
Yeah. So the other question, before I take a question from the Q&A is, so the Oracle uncertainty. So you were saying that we should not take a decision. We know sometimes for sure that this is something we don't want the agent to follow. But always Oracle uncertainty always exists. So
right.
So what are the ways? Are there any theoretically rigorous ways in which there are Oracle uncertainties being handled, or is it based on heuristics?
Right, that's a great question. So first, two things, right? So first, human is not an oracle in my head. Human is an ally. Human makes mistakes. We know that. Both so like when they give you a demonstration that is incorrect, I can for sure say that some of the advice is incorrect because Jay generalized a lot, right? So everybody, when I came to US, 20 years back, I was told by everyone, oh, everybody there drives a BMW. Okay, I don't drive one, right? And so that's these kinds of things that this generalization knowledge that people give you, they are not always true. So first, I want to make sure that I clear that thing that I'm not assuming an oracle from a human. I'm assuming that the human is incorrect. So now that we established that, the uncertainty of the human basically means that all I need is two different models. One to model the demonstration, the data uncertainty. The other is the human advice or knowledge uncertainty. Let me just call it knowledge uncertainty. So, and what we have shown, first, yes, there are heuristics to simply do that by simply weighing them one over the other. The other one is explicitly learning the model. And so what we have done is we have built two different types of probabilistic models, one for modeling the data uncertainty, one for modeling the knowledge uncertainty, and then figuring out what an efficient combination of them could be. Maybe something like an EM algorithm that could combine. Like, so think of like a mixture of Gaussians, but I do that from the perspective of two different densities, one coming from data, one coming from knowledge, and then combining them. So I mean, there are principled ways to do that. I'm just saying one way that we have done that. Of course, meta learning is another thing. What if I give you explicitly trying to predict when they are going to be wrong, and then use that to reason when you are learning? So I mean, that's an extremely important and relevant question, and I think, yeah, that can be solved.
Yeah, so I just will take one question from the audience. The question is, what are the ambiguity versus risk in sequential decision making, from Mubarak Ali?
So the ambiguity versus risk, I mean, there's always ambiguity, because in sequential decision making, most of the time, it's the unknown that matters, right? I mean, you don't know if you open the door, there's a gold or there's a tiger behind, right? So the point is that that's where the ambiguity is always there. Like this, instead of ambiguity, I'll call it uncertainty. And there's always that uncertainty, right? Ambiguity occurs because of sensor noise, data noise, and so on. So let's talk a little bit more general in terms of the uncertainty itself. And that can occur due to the noise. Yes, that's one source. But it could also be the gap in knowledge that we have. And the risk, yes, that is where we have to explicitly evaluate how much worthy is it to explore this state that I do not know, when there is a chance of a risk, right? So let's say, okay, if I jump from top of the mountain and I don't see anything, I just see some clouds, am I going to land on rock, or is it going to be just like a new nice feather bed, right? Who knows, right? But the question is, there are some cases where you don't want to do that because the risk associated is much higher, and there are some doors you don't want to open, and that we call it intuition, and that's a great question, and that's what we are trying to figure out. How can you do that intuition? How can you bring that in to the learning algorithm? So I think you said Mubarak, right? So I don't have an answer perfectly to that, but that solving that, resolving the trade-off between what we know and what we don't know, that know don't know, and the risk of knowing what we don't know. And I think that is where everybody is different, right? So for instance, I always use this, and my dad gets a laugh every time I say this. My dad never leaves to an airport less than 3 hours before the plane departing. Okay, he has to be there in the airport 3 hours before, no matter what, COVID, no COVID. And they live like 3 kilometers from the airport in India, right? In Madras, they live 3 kilometers from the airport, but they still leave 3.5 hours early, right? So he doesn't want to know. He's always risk aware, and that risk averse rather, that he doesn't want to know what is going to happen if I go late, right? On the other hand, I have a friend who doesn't leave to the airport 1 hour before the flight departs, no matter where he is, and he has missed many flights. And so we humans do that all the time, right? There is a risk versus what am I going to get in terms of the uncertainty? And I think that question is completely open, and I don't think we can easily solve it, because face it, we two humans don't agree. When two humans don't agree, we're not going to agree to the solution of the learning agent as well. So, but that's definitely one of the top questions inside RL, inside sequential decision making rather.
Yeah. Thank you so much, Professor Sriraam.
Thank you so much. Thank you.
And before I close the session, I would like to announce that there is a spotlight on IITM research after this, where IITM